Hello and welcome to the 8th lecture for Math 155. We're now going to be moving on to a new section of the course where we talk about functions with multiple variables. There are lots of applications for functions of multiple variables. This outline page shows an example of where if you have a position given by, say, x and y coordinates, or in this case latitude and longitude on a map, we can talk about something like the temperature at that particular location. So we're going to be talking about different terminology related to functions of multiple variables, starting with function, what we mean by its domain, and that's essentially what is the input for a function, the set of variables that we can put in to that function, and its range is the set of outputs that it produces. The notion of a graph will be familiar to you, but now we're moving into multiple dimensions. If we just say have two dimensions, our graph becomes a surface, whereas previously we'd be graphing lines or curves for functions of one variable. And then also this idea of a level curve. Well, you would have met level curves in your day-to-day life before. When you look at, say, a graph of or a map of temperature like we have here, the level curves are the curves which, when you move around those curves, your function doesn't change. So in this case, your temperature doesn't change. You'd also see this if you look at a map and you look at contours for height on that map. The contours show where the height doesn't change. So you would have met it before, but maybe not in this context of being called a level curve. Okay, so first of all, we say if we're thinking about a function of just two variables, a lot of this will apply to multiple variables, but we're just going to focus on two variables here. We say that a function f of two variables is a rule that assigns each ordered pair of real numbers. So the ordering matters. We can't just switch those order around. So you have an ordered pair of real numbers x, y in some set D. So D could be, say, all of the real numbers. It could be just positive values of the real numbers. Whatever happens to be that set D, we take any ordered pair of real numbers within that set, and we get an output, which is a unique real number denoted by f of x, y. So f is our function that we're applying to our ordered pair x, y. D is called our domain. So domain is, think of that as the input, and the range of f is the set of values that it chucks out. So that's its output. So we write the range down as this set here. So this is the set. So the set is denoted by these curly braces here. So it's the set of f of x, y, so all the function outputs. This vertical line here just means such that. So it's the set of all f of x, y such that x and y are in the domain. So the ordered pair x, y is in the domain. That's all that notation means. So as an example, if you want to work out your body mass index, your BMI, this is defined to be B of mh, where m is the person's mass in kilograms, and h is their height in meters. So our function is we take the height and we divide it as the mass, sorry, and we divide it by the height squared. So if we have a person who weighs 64 kilograms and is 170 centimeters tall, what's their BMI? Well, their m is going to be equal to 64. Note that the height was in meters, so we need to convert this to centimeters. So this is h is equal to 1.7. Okay, so what do? Well, we write down b of the mass, which is 64, the height, which is 1.7 meters, and that's just going to be 64 over 1.7 squared, which is approximately 22.15. So this is just a way in which we can plug numbers into this formula, into this function, and we get an output, which is a real number here. So note that the domain in this case, it would only make sense to have non-negative values, or in fact, it would only make sense to have positive values here for our mass and for our height. Okay, so every person has a positive mass and a positive height, so we wouldn't be able to put in negative numbers. So our domain here would be the set of all positive real numbers. We can also think about functions of multiple variables by just looking at numerical tables like this. So if we want to work out what the wind chill index, in other words, how cold it feels when you're outside, that depends on both the speed of the wind and the air temperature. So if we denote the temperature as capital T and the wind speed as W, then our function of the wind chill, capital W, is equal to F of TW. We don't actually know what that function is here, but say we have a temperature of -5 degrees and a wind speed of 25 kilometers an hour, we can just look at this table to work out what our wind chill is. So we need to look at this row here, because that's when we have -5 degrees. And we need to look at this column here, which is when we have wind speed of 25 kilometers an hour. Okay, so W, our wind chill, W is equal to F of TW, so T is -5 and W is 25. Well, we can just read it off here. It's going to be -12. So it's this entry here at the intersection. So we've already seen, therefore, a couple of different ways in which we can talk about functions of multiple variables, or in which we can represent them. We've just seen on the wind chill example that we can do this numerically by using a table of values. We could also do this algebraically, as with our body mass index formula. So we have a formula there, and we can write that our function down as a function of two variables and write down exactly what the relationship is that chucks out the number at the end. We could also just describe a particular relationship. I could have described the body mass index in words rather than by describing it with an explicit formula. And we can also describe things and represent them using visual representations. So we could use a graph or a level curve. So this example on the right-hand side, suppose we have whatever values for x and y. So suppose we take a value a, this could be anything. So suppose we take a value a for x and value b for y. So these are our inputs somewhere in this xy plane here. And then what we need to do then is look up to the surface, so somewhere around about here, which, if I use these reference lines here, just to map it back to the height C here, which is going to be f of AB. So that's just going to be what our function was. We can also look at these level curves that I mentioned at the start. So think of these as being things like contours on a map representing the height. So these level curves that are projected down onto the XY plane tell us when our height is equal, first of all, here, when the height is equal to 45 or 40 or 35, 30, and so on. So here we could roughly tell that, well, we're just below this level curve here, where k is equal to 25. In other words, by the output, our height is 25, and we're above this one here, where our output is 20. So our height is 20 here. So we're somewhere between this bit here and this bit here, and closer to the blue level curve that I've indicated. So that applies for any value around this surface at that same level. So we could say here, okay, our output, our C is equal to F of AB, is going to be approximately 23, 24, something like that. Okay, so we could look at these things using graphs and level curves as well. So in general, we say that F is a function of two variables with domain D. Then the graph of F is the set of all points X, Y, and Z in R3, now, rather than just being in R2, such that Z, the Z coordinate, the height is equal to F of XY, so F is our function here, and XY is our domain. So all we're doing is we've got some points in the XY plane, and then we work out the height based on the function F of XY. Okay, so that's exactly what's going on in this graph above. And then a level curve is going to be any point, for any value of k, so k could be any number, any constant, that's going to be the curves that have the equation f of x is equal to k. Okay, so all of these curves up here, the k values are just f of xy is equal to 20 or 25 or 30 and so on. So as you move along any of those curves, your function f of xy doesn't change its output value. it remains the same. So those level curves can be really useful for telling us something about when values change or how quickly they're changing. Because if your level curves are very close together, that means that your values are changing very quickly. Whereas if in other parts of your output, if they are changing very, your level curves are very far apart, that means that your values, your gradient is changing slowly. Okay, and we'll talk more about gradients in a future lecture. Okay, so let's go through an example. Suppose we've got this function f of xy is equal to 6 minus 3x minus 2y. So let's sketch some level curves. Okay, so what's this going to look like? Let's first of all put on some axes. So suppose this is my x and y axes, and I'm just going to put some values on here. Okay, 1, 2, 3, 4. Okay, so we want to sketch level curves, so we want to have f of xy is equal to some value k as we vary k. So k is just a constant we're choosing. So for example, let's suppose we choose, first of all, let's go for k is equal to 0. Well, this means that we can just have 6 minus 3x minus 2y is equal to 0. So we want to draw this, this curve, and this just turns out to be a straight line. So we can rearrange this for y. So this is the same as y is equal to minus 3 over 2x plus 3. Okay, so just rearranging that for y. So this is just a straight line that goes through, first of all, when x is equal to 0, y is equal to 3. So it goes through this point here. And when y is equal to 0, x is going to be equal to 2. So we can now draw a straight line. This is the level curve here. That's the level curve when k is equal to 0. Okay, what about if we pick another value? Suppose we set k is equal to 2. Well, now we're going to have 6 minus 3x minus 2y is equal to 2. We can rearrange that to be y is equal to minus 3 over 2x plus 2. This is going to be a curve that is, or a line in this case, a straight line that's going to be parallel to the other one that we've already drawn, but now going through 0, 2. So when x is 0, y is equal to 2. So this is our level curve. We have k is equal to 2. And we can keep drawing on other level curves here. So if you do that, you'll find that your level curves when k is increasing, going this way, so k increases, we end up with more straight lines go in that direction, and with k decreasing, they go in that direction. Okay, so what this is saying then is if we move our x, y values that we're putting in anyway in this direction, then our output of our function is going to be decreasing. If we move them anyway in this direction, then the output is going to be decreasing. And if we move along any of these curves here, then our output is going to be fixed. Okay, it's going to be constant. So if we move anywhere along this green line, the output of our function is going to be always equal to 2. We can plot these sorts of functions on Math 3D. So here is an example of this function that we just had here plotted. Let me just move that over here. So if you go to the math3d.org, if you want to plot a surface, you just go to add object and then explicit surface, and then you can type in your function. And we see here that this is the function that we've just plotted now. Okay, so you can spin this around. It's a little bit clunky on this, this tablet that I've got. You can spin that around and see what's going on with these functions and get a bit of an intuition as to what those level curves actually mean. Okay, let's think about another example. Suppose now we've got the function f of xy is equal to x squared plus y squared. So what are the level curves going to look like in this case? Well, again, let's draw some axes just to start with. So we want to sketch our level curves. What happens if we've got, first of all, k is equal to 0? Well, in that case, we've got x squared plus y squared equal to 0. So that's just the point x is equal to 0, y is equal to 0. So those are the only values that satisfy that. So in that case, our level curve is actually just this point here, corresponding to the curve k is equal to 0. How about if we have a different value? So suppose now we've got k is equal to 1. So this is x squared plus y squared is equal to 1. And that's just a circle of radius 1. So a circle of radius 1 centered at the origin. Okay, so that looks something like this. So that passes through this point 1 here. So that's, sorry, not k is equal to 0, that's k is equal to 1. And just one more example, if we say looked at k is equal to 4, well, that's the level curve x squared plus y squared is equal to 4. And that's just a circle centered at the origin again of radius 2. So that is a circle that looks something like this. So this is the level curve for k is equal to 4, and it passes through x is equal to 2 there. Okay, so this is another example that, again, we can just plot this on Math 3D. So if we now look at what this looks like, again, we can use exactly the same setup here to draw this level curve. We just go to add object, explicit surface, and then type in what our surface is. So in this case, x squared plus y squared. And we can see here that we end up with this sort of cup shape here. Again, it's a little bit clunky in terms of the rotation here. But we can end up seeing that we've got this cup shape here. So we've got this x squared plus y squared function. For any value of x and y, values of x, y ordered pair that we put in, we end up with this cup shape here. We can also add on a level surface here. So we've got all values where x squared plus y squared is equal to 2. We can see that intersects through here. If I manage to go above or below, we can see that this is the same as a circle. Okay, so we ended up with circles in our level curves in our sketches, and this is exactly what we get if we think about a level curve here. That's just going to be a circle. So we've got these concentric circles going up for this function. Okay, so the last thing to talk about today is the domain and the range of a function. Okay, so suppose we've got this function here, g of x, y is equal to the square root of x plus y plus 1 divided by x minus 2. Now, if you recall from the beginning, we've got the domain is all values of x and y, which makes sense to plug into g. What I mean by this is that we don't want to plug in values into our g that don't make any sense. So, for example, here, if we look at the denominator, we can't divide by 0, so we know here that we can't have x minus 2 being equal to 0. So we need x minus 2 to not be equal to 0, which implies that x can't be equal to 2. So we know that x is equal to 2 is excluded from the domain of this function. And we know from operating with the square root that when we've got real numbers, we can't take the square root of a real number that's negative. Otherwise, we end up with an imaginary number, which we'll talk about later in this course. But for the purposes of here, we just want real numbers outputted. So we need the square root of x plus y plus 1 to be greater than or equal to 0, which implies that we need x plus y plus 1 to be greater than or equal to 0. So if we just square both sides and then rearrange, we need y to be greater than or equal to minus x minus 1. So here the domain, call this our domain D, is going to be the set of all x, y pairs such that, remember that vertical line means such that x is not equal to 2 and y is greater than or equal to minus x minus 1. So we can visualize that. Suppose we draw our axes like this. These are our x and y axes here. And we can think about these lines that we've just found. So we know that y has to be greater than or equal to minus x minus 1. So that means that we can't have values below this line here. So this is the line y is equal to minus x minus 1. So this is minus 1 here. So that means that we can only take values above that. And we also know that we can't have any values where x is equal to 2. Okay, so we can exclude that red dashed line there. So the only values that we can end up taking are values given by this shading here. Okay, so everything above that line, that blue diagonal line, except for values where x is equal to 2. That gives us our domain. And then our range. So ranges tend to be harder to work out, but we can plug certain values in to think about the types of outputs that we get. So for example, for our range, if we first of all consider what happens if we say take g of 3 and any value of y, so we're going to fix our value of x, a particular value here, 3, and we're going to vary y. This ultimately just gives us the square root of y plus 4. And this can take any value between 0 and infinity, okay? So the range of this, if we restrict ourselves to fixing x is equal to 3, this gives us a range between 0 and infinity. And then if we think about g of 1y, so now we're going to fix x is equal to 1, this is just equal to minus square root of y plus 2. Okay, and this now has a range, this is negative, so this has a range going from minus infinity to 0. So therefore this tells us that we can make any value by varying our values of x and y to go between minus infinity and positive infinity. Okay, so we can therefore say that we can put these two things together, g of xy has range real numbers r. Okay, that's it for most of the material here. Make sure you understand these different terms, what a function is, what the domain and range are. The domain, remember, is the input essentially, and range is the output. What we mean by graphs of when we have functions of two variables, and what a level curve is. Okay, thanks very much. Bye.